Okay, Bismillah ar-Rahman ar-Rahim. My name is Khalid Al-Awam. I will be doing a presentation on Introduction to Respiratory Anatomy and Physiology. And this is going to be extremely fundamental for understanding the remaining webinars that you're going to be listening to. And, you know, a fundamental understanding of respiratory anatomy and physiology is very important for the management of patients who are suffering respiratory diseases. Our presentation, objectives for the presentation include looking at the structures that make up the respiratory system. We're going to look at how the respiratory system processes oxygen and CO2. We're going to look at a comparison and contrast of the function of the upper versus the lower respiratory tract systems, and we're going to look at alveolar capillary units, which are fundamental units for the gas exchange, one of the primary functions of the respiratory system at this point. And we're going to look at the transport of gases through the conducting airways to and from the alveoli. We'll look at the characteristics of the airways, just a brief look at the characteristics of the airways and what importance does that play in terms of function. And we're going to look at the components of the chest wall and how it relates to the function of the muscles of respiration and how actually we breathe in and out and manage to get the gas from the external environment to our alveoli. So the general function of the respiratory system has two primary functions, but it has also ancillary functions that we also have to remember. But one of the primary functions of the respiratory system is the exchange of gases. And the exchange of gases happens in two ways that we're going to explain a little bit later. But exchange of gases between the atmosphere and the blood, and then from the blood to the tissues. Other primary functions of the respiratory system include regulation of pH, which is dependent on the rate of CO2 release. And we know that the CO2 represents the respiratory component of the acid-base balance. Respiratory system plays an important role in protection of the body from foreign bodies by trapping them in the upper airways. And if they eventually reach the alveoli, then there is also an extra mechanism for protection that is inherent in the alveoli. We cannot speak without the respiratory system. That's a well-known fact. The larynx contains the vocal cords, which are very important for vocalization. Respiratory system is also involved in many synthesis and activation of a whole host of products and hormones in our body, one of which is leukotrienes and angiotensin as well. And these are important functions that are inherent in the respiratory system. Now, the respiration is a series of exchanges that leads to uptake of oxygen by the cells and the release of carbon dioxide to the tissues. While this might be a general statement, this involves a variety of steps that have to be understood. Step one starts with the ventilation. So the first step that we need to do is to bring the air from the outside environment into our lungs. And that outside air or atmospheric air contains the oxygen. And then the next process is expelling or exhaling the CO2-rich air out into the environment. Step two is the exchange between the alveoli and the lung and the pulmonary capillaries, primarily known as diffusion. But that process of gas exchange between the external environment and our blood in the lungs is called external respiration. Then once that happens, then the next step, which is step three, is to transport gases in the blood. And once these blood gases or these gases reach the cells, the next step happens, which is the exchange between the blood and cells itself, which is referred to as internal respiration. Obviously, the cells take up the oxygen and use it to process energy in the form of ATP synthesis. Without that, the body would have to resort to anaerobic metabolism, which is a very complicated process that may lead to accumulation of acids in our body. But if the blood that reaches the alveoli, the cells is rich with oxygen, then the cells would resort to aerobic metabolism, producing enough and sufficient energy for our body. Here is a beautiful diagram that shows the difference between external respiration and internal respiration. And you can see here at the top of the graph where we have the exchange between the alveoli and the capillaries in the lung, and that represents the external respiration. And you'll see that here the blood takes on oxygen from the alveoli, and the venous blood gives away CO2 to the alveoli, and then the alveoli eventually exhale it out. Now, when we move to the internal respiration, when this oxygen-rich blood reaches the cells would start the process of taking on oxygen and giving away CO2 to the systemic capillaries, and that CO2 would eventually be transported back to the lungs where it would be exhaled out. Now, we have to understand that the respiratory system has variable structural aspects, and each structural aspect has a functional aspect to it. So a basic understanding of these structural aspects will help us understand the functional aspects. So we know that the respiratory system is made up of, a number of divisions. The first one is the conducting portion, and that would represent the upper airway, so starting with the nose all the way down to the bronchi. And then we have the exchange portion, which would be represented by the alveoli and the capillaries in the lungs. And then the structures involved in ventilation include the skeleton and musculature, which are important for the movement of gas in and out of our lungs. The pleural membrane plays a very important role by maintaining a constant negative pressure in our chest, which would make it easy for us to breathe in and maintain our lungs at an inflated state and prevent it from collapsing. Then we have the neuronal pathways, which serve as a biofeedback mechanism, an efferent, an input mechanism to our central respiratory centers that would modulate breathing in case there are changes. The respiratory system is divided primarily into upper respiratory tract, which is the, from the nose all the way to the entrance to the larynx. And then we have the lower respiratory tract, which is the larynx all the way to the alveoli, or to the lungs itself. And here is a beautiful diagram that shows the division that happens. If you look at the larynx and up, that's called upper respiratory. If you look at the larynx and at the bottom, all the way to the alveoli, then we call that the lower respiratory system. Now, the bones and muscles and membranes are very important, as I mentioned previously. Now, we have the primary muscle of breathing, which is the diaphragm. That diaphragm is the primary muscle of breathing. Once the diaphragm contracts, it pulls on the pleural membranes of the lung that are maintaining, as I said earlier, a negative pressure. And when the diaphragm pulls on them, that helps create an even more negative pressure, creating a pressure gradient between the inside environment, which is the thoracic cavity, and the outside environment, which is the air we are breathing. And that would permit the gas to flow into our lungs. Now, inspiration or inhalation is an active process requiring the diaphragm to contract. However, expiration or exhalation is a passive process where there is no energy requirement, and that's some of the blessings from Allah subhanahu wa ta'ala, giving us a vital physiological mechanism that needs only one type of energy, or energy in one direction. However, the second direction, which is exhalation, does not require energy. And this is, important for patients who are breathing normally, and then it becomes also important for patients who are on mechanical ventilation. There are also accessory muscles of breathing that can be used during inspiration or expiration. For example, we have the sternocleidomastoid muscles here, we have the scalene muscles, we have the internal intercostals, we have the external intercostals, and we have the abdominal muscles, which would be activated in case there is an increased work of breathing or an increased respiratory demand for patients who are sick. Now, the functions of the bones and the muscles and membranes are very important. They create and transmit a pressure gradient, like I said, relying on the attachment of the muscles to the ribs, and that is very important, and the overlying tissues. And then the attachment of the diaphragm to the base of the lungs and associated pleural membranes. And there is tiny ligaments that attach the pleural membrane to the diaphragm. And when the diaphragm contracts, it acts on pulling the pleural membrane down and allowing that difference in pressure between the inside and the outside and allowing the gas to move in. The cohesion of the parietal membrane to the visceral membrane is very important here. And there is what we call a potential space between the two layers of the pleural membrane. And that potential membrane is extremely important for making the lung float over each other without having a friction. And this is, if you remember, or if you will see later on, that this is the site where we would have pleural effusions or pneumothoraces if that membrane structure is penetrated. Expansion and recoil of the lung, and therefore alveoli, with movement and of the underlying structures is very important. The lungs or the alveoli will respond to changes in pressure, and those changes in pressure will help inflate the lungs and therefore permit a volume to be to fill them up and create the movement of gas from the outside environment to the inside environment. And there is a whole host of physical or physics laws involved here that help create that difference in pressure and therefore permit the gas to move in and out. The loss of these physics laws could hinder the performance and the function of the respiratory system. Now, we know that the cohesion between the parietal and visceral layer is very important because there is that tiny serous fluid in the pleural cavity, which is about 30 ml of fluid, which creates an attraction between the two sheets of the membrane and maintain them sort of stuck to each other. And as the parietal membrane expands due to expansion of the thoracic cavity, it pulls the visceral membrane with it and then pulls the underlying structure, which expands as well. Now, the underlying structures here would be the alveoli. So when there is a change in the negative pressure within the pleural membrane due to movement of the diaphragm, it will transmit that change in pressure to the alveoli, and the alveoli's pressure now becomes less than the pressure compared to the outside environment, and therefore permits the movement of air from the outside to the inside. Now, if there is a disruption, like I said before, of the integrity of the pleural membrane, it will result in rapid equalization of pressure and therefore the loss of ventilation function. And you could have a case like a pneumothorax where you have air leaking into the pleural cavity and disrupting that maintain the negative pressure. And instead of negative pressure, you would have positive pressure, which would lead to collapse of the lung and leads to a condition known as a pneumothorax. Here is a very nice picture that shows you how these membranes overlap the lung. They cover the lung all around, both lungs. Both lungs have separate cavities for them. And like we said, there is a parietal layer and there is a visceral layer. And in between them, there is this potential space that contain a minor amount of serous fluid, which is extremely important for preventing friction between the wall of the lungs and the wall of the thoracic cavity. And maintenance of that that membrane is extremely important for the normal function. Having that pleural membrane surround our lungs ensures that we have something called functional residual capacity, which is a very, very important concept when it comes to, respiratory physiology. Loss of this functional residual capacity due to disruption of the pleural membrane could lead to a whole host of pathological problems and disruption of the respiratory mechanics, making it very difficult for the patient to breathe. Now, if we go down a little bit down, and we talk about the tracheobronchial tree, which is connecting the external environment to the exchange portion of the lung. And they are similar to a vascular component. I always say that they look like a tree. If you look at an upside down tree, you have the stem of the tree and then you have the branches. And if you look at a tree without leaves, then you're looking at a tracheobronchial tree. And it has a larger airway, which have a higher flow and velocity, but they do have a small cross-sectional area. And therefore, the resistance or the airway resistance in the upper airways is way higher than the resistance in the lower airways. The lower airways or the smaller airways, they have lower flow and lower velocity, but due to their large cross-sectional area, they have very low airway resistance. But however, if they become narrowed due to any pathological problems such as inflammation or bronchoconstriction, that could lead to an immense increase in airway resistance and creating difficulty for the patient to breathe. And here is a beautiful comparison looking at the differences between the upper airways and the lower airways. If you can see here, when we look at the particles that are trapped in the upper airways, they're usually the larger particles that are trapped in the upper airways. And then as we get to the smaller airways, then we get smaller particles. Now, these smaller particles, if they manage to get all the way down to the lungs, then there is an extra defense mechanism, primarily by phagocytosis, to remove them. And if you look at the smooth muscle, when you look at the smooth muscle structure of the upper airway versus the lower airways contain more smooth muscles, and therefore those patients, for example, with asthma would have a more constricted lower airways, and that make it difficult for them to breathe. Whereas the upper airway maintain or have cartilages, and these cartilages keep them open in a much better way. You can see that in the upper airway, the air velocity is higher, whereas in the lower airways, the air velocity is lower. And then we have to think about the cross-sectional area being the biggest determining factor when it comes to movement of gases from the upper airways all the way to the lower airways. The lower airways, there's so many of them. And when you put all them together, the cross-sectional area becomes very, very high, and therefore makes it easy to distribute the air to all these smaller or what we call respiratory units where gas exchange would occur. Now, the upper respiratory tract is for all intents and purposes as a single large conducting airway. It's the primary airway. It's all where the flow is gonna go through. We call it bulk flow. For example, we have only one trachea, so all the air we breathe in is gonna flow through the trachea. The lower respiratory tract, however, starts after the larynx and divides again and again into multiple divisions, and then creating smallest regions which form the exchange membrane. So if I go back to my example of the tree where we have branching and branching all the way until we reach the leaves, for example, the leaves would represent the alveoli. Now, if you want to trace and see how gas flow from the upper airways all the way to the lower airways, we start, like I said, at the trachea. Then we have the primary bronchi, which are the right and left. Then we have secondary bronchi, which branches into lobes. And then we have tertiary bronchi, which branches into segments. Then we have bronchioles, which is subsegments. Eventually, we get to terminal bronchioles. And all of this area, trachea, primary bronchi, secondary bronchi, tertiary bronchi, and bronchioles and terminal bronchioles don't have any gas exchange. The gas exchange starts at the respiratory bronchioles with the start of the alveolar outpatches, or what we call alveolar ducts, and then we have eventually the alveoli. So respiratory gas exchange starts at the respiratory bronchioles, but the primary gas exchange obviously occurs in the alveoli. Now here's a beautiful diagram showing the trachea, and then we branch into this lung here where we have an upper lobe, a lower lobe, and then we have branching all the way to the bronchioles. When we reach the respiratory bronchioles here, we can see that here is gas exchange area. All the other areas up here, we call them conducting airways, and we refer to them as anatomical dead space. And we refer to them as dead space because there is no gas exchange. From the respiratory bronchioles onwards, that's considered where gas exchange would occur. And when you reach the alveoli here, you can see the branching. We have about 23 to 24 generations of branching all the way before we reach the alveoli. And this is extremely important to widen the surface area and to accommodate the massive number of alveoli. We have about 300 million alveoli in our lungs, and you need to have this extensive subdivision so you can reach all the way down to the alveoli. Once you reach the alveoli, then you have this beautiful circular shape, and that circular shape is very important in the alveoli to create a larger surface area for gas exchange. Now, like I said, when we reach the alveoli, which is the site of gas exchange, the surface area is rather massive because of the fact that they are thin-walled and they are packed next to each other, and you have about 300 million alveoli. Again, a physical principle applied here is Fick's law, and Fick's law says rate of diffusion increases with surface area. So when you have 300 million alveoli packed into your chest, and you try to calculate their service area. Their service area is approximately 70 square meters, or about the size of a tennis court. So that, you know, massive surface area is very conducive for, you know, normal and exceptionally high rate of diffusion or gas exchange between the alveoli and the capillaries. Each alveoli is surrounded by approximately 300 pulmonary capillaries, and this is extremely important to enhance the diffusion process or the gas exchange between the external environment and the capillaries. Now, function of the upper respiratory tract is very important here. We have lots of functions that are extremely important, one of which is to warm, humidify, filter, and we said vocalize. Now, our body needs what we call homeostasis, which is normal environment. So if you're living in a very hot environment and you breathe very hot air, your body has to work on, you know, fixing that warm air and making it, you know, regulated to body temperature. And vice versa, if you live in a very cold environment, your body has to work on also fixing that and bringing it to normal body temperature. Humidity is also another factor. If you're, the respiratory system is one of the systems that is open to the external environment, so it's subjective to being dried out. So our nose is very extremely important function is to, you know, humidify this air and ensure that by the time it reaches about half the trachea, it has 100% humidity. Now, filtration is very important. That filtration process happens very importantly by the mucociliary blanket here, where any foreign particles that don't get trapped by the upper airways, when they reach the lower airways, we have this mucus, and that mucus acts as, you know, a sieve of, you know, for cleaning up our lungs and trapping any dust or microbes or viruses that would reach the lower airways, and, you know, through the process of ciliary movement, the cilia movement, expel them all the way up to the upper airways, where they get, we either cough them out or we swallow them to ensure that our body stays clean and, you know, microbe free, I guess, if you want to say it that way. And another function that is extremely important is the vocalization. You know, the loss of the vocal cords would mean that we would not be able to speak. And patients who are intubated, for example, are unable to speak because we have bypassed the vocal cords. And that's a very important structure that is located in the larynx. Now, the function of the respiratory tract is the exchange of gases due to, like I said, huge surface area. 10 to the 5 square meter, or what represents about 70 square meters. Okay, and there is the associated network of pulmonary capillaries. As I said before, each alveoli is surrounded by approximately 300 capillaries, and that is very important for the gas exchange process. Now, the layer or the membrane that separates the alveoli from the capillaries is a very, very thin membrane. And the thickness is approximately 1 micrometer. And that thickness is very important for enhancing or improving the gas exchange. If a patient develops pulmonary edema, or if there's thickening of that membrane, gas exchange process would be hindered, and the patient may start having problems. So this is extremely important. Like I said, if there is any microbe or any foreign body that manages to reach the alveoli that has not been trapped by the previous, you know, defense mechanisms in the upper airways or in the lower airways, then the alveoli contain specific cells called macrophages, and these macrophages, their function is to engulf and clear up any foreign materials that would reach the alveoli. In between, or in the corners of the alveolar cells, there is another type of cells called type 2 alveolar cells. And these are very important cells because they produce a very important substance called surfactant. And that surfactant has the primary function of lowering surface tension, or the adhesion between liquid molecules. And when you lower the surface tension, you keep the alveoli open and you maintain them in the functional residual capacity state, as I mentioned before. And it improves and maintains the lung open, prevents them from the collapse. If there is any condition that would derange or affect the surfactant production, the alveoli would collapse, and then we would have major problems, that the patient's respiratory work of breathing would increase, and then patient may even have to be put on a ventilator. So the structure of the lower airways, as I mentioned previously, you have these beautifully rounded alveoli that are packed next to each other with very thin membranes separating them from the capillaries. And you can see that on the side here, the extensive network of pulmonary capillaries that surround each alveoli, and that is very important for ensuring optimal gas diffusion, and therefore optimal gas exchange and normal oxygen level and removal of CO2. Now, when we look at the characteristic of the exchange membrane, we have high volume of blood through the lung, which is very important. You have a fast circulation through the lung. The entire cardiac output of 5 liters per minute is pumped into the lungs, and then once the gas exchange occurs, it converts into the systemic circulation, where there's also a 5 liter per minute, which goes to the body. Now, the pulmonary circulation would be bringing in the oxygen low, CO2 high blood, and then the systemic circulation would carry the oxygen high, CO2 low back to the cells. And blood pressure is low in the lung, which is very important. And that lower hydrostatic pressure is very important to prevent the fluids from leaking from the capillaries into the alveoli, and to ensure that the lungs don't get flooded with fluids. And that's very important to ensure that there is no pulmonary edema or interstitial edema. That low blood pressure is very important for maintaining the fluids within the pulmonary circulation in their place, preventing them from moving from the capillaries into the alveoli. And if there is any movement of a minor amount of fluid, then you have the lymphatic system, which would be in charge of removing any extra fluid that would leak there. Any imbalance to that, to that mechanism would lead to increased filtration. And if there is increased filtration, the fluids would end up in the alveoli or between the alveoli and would lead to a condition known as pulmonary edema. That's it for today. I hope that I presented, with you with full information, and thank you so much for the chance to participate.